Hello everybody. In this video, we'll be going through question 6 to 10 of the SMO Senior 2020. Jumping straight into question 6, it contains 3 absolute values, which looks like a bit of a disaster since we know that absolute values give us 2 cases and having 3 of them gives us a lot of cases. The one saving grace here is that we are not really asked to find solutions to an equation. We are only asked to find the minimum possible value. Finding the minimum possible value turns out to be quite simple if we understand how these kind of graphs look. X minus 10, x minus 20, and x minus 30 inside absolute values means that they turn from negative to positive at 10, 20, and 30 respectively. So I'm going to draw a number line. And on this number line, I'm just going to mark out 10, 20, and 30. In theory, we could find out what this function looks like in each of these 4 smaller intervals, since we can take out the absolute value sign and determine is it positive or negative accordingly. So for example, if we just looked at the one on the right, it would become x minus 10 minus x minus 20 plus x minus 30, since all of them are positive, and this is equal to x minus 20. Now we could repeat this 3 more times if we so desired, look for the minimum value in each interval and compare across them to find the overall minimum. That is certainly acceptable, but we can notice something else to save us a bit of time. All of these 3 intervals, and the 4th one as well, will be all some linear something, and whether it be increasing, decreasing, we just know that it is linear. That means that your graph consists of 4 straight lines being glued together. So your graph, and I don't really know how to draw the graph because I don't know much about 10, 20, and 30 and everything in between, but I know that it is going to kind of turn around or at least change direction at 10, 20, and 30, but other than that, just be 4 straight lines. So for instance, maybe it looks something like this. Maybe it looks something like this. Now I really don't know how it looks like without checking each of these cases, but that is enough to tell me I only need to check the minimum. If it occurs, it must be at 10, 20, or 30. Because it can't occur somewhere in the middle of a line. Technically, it could also happen as you go to plus or minus infinity, but that's not really possible for a question that asks you for a minimum value, which shouldn't be negative infinity. So it has to be either 10, 20, or 30, and you just check it. So you check x equals to 10, x equals to 20, and x equals to 30. If we substitute them in, we would respectively get 10, 20, and back to 10. So that means that the minimum value is just 10. What I've mentioned here has allusions to critical points in calculus. So for those of you watching who know what are critical points, you realize that 10, 20, and 30 are critical points simply because the function is not differentiable at those 3 places. And therefore, we don't need to look at any other place apart from 10, 20, 30 and the limits to plus and minus infinity. If you're not familiar with calculus, it's okay. I think the graph is good enough for you to get a decent picture of this idea. Next up is question 7, which is our first geometry question. We have a parallelogram ABCD. AB is 39 and BC is 25. We also have one of the diagonals, which is 34, and we are asked to find the length of the other diagonal, AC. Now, based on the question, you don't actually just know that AB and BC are 39 and 25. Since we are working inside a parallelogram, we know that the opposite sides are also equal. In other words, the only length we do not know is the length of AC. So what we can do if we wanted to find AC would be to try to find an angle which would tell us AC, such as angle ABC, and then to use the cosine rule to get AC. So let's call this angle theta. We want to find out the value of theta so that we can get AC. Well, the other information we have is the opposite diagonal is 34. So we can use the cosine rule as well to find the other angle, which will be 180 degrees minus theta. And so immediately this tells us our plan. Find cosine of theta using cosine of 180 degrees minus theta, and both of these would be linked to the cosine rule. So now let's just work out the computational details. Firstly, if I have triangle DAB, then 34 squared equals 25 squared plus 39 squared minus 2 times 25 times 39 cosine of 180 degrees minus theta. And we also have the other triangle, ABC, and it tells us that AC squared, which is what we want, is equal to 25 squared plus 39 squared minus 2 times 25 times 39 cosine theta. Remember that our plan was to find cosine 180 degrees minus theta using the first equation, and then use that to jump to cosine theta, and then from that find AC. However, once we look at these two equations, we can tell that it is going to be a little bit annoying if we had to do that many calculations. So to speed things up a bit, we can observe that these two, cosine 180 degrees minus theta and cosine theta, are negatives of each other, since theta and 180 degrees minus theta are just reflected over the y-axis in your unit circle. And that means that if I were to add these two equations together, the last term in both equations will cancel out. So let's do that. We can sum the two equations. 34 squared plus AC squared becomes 2 times of 25 squared plus 39 squared. So at this point, I'll leave you to do the calculation on your own. However, it would simplify to AC is equal to 56. So this is actually an identity that holds for any parallelogram. Let me write it down at the top. Since all of the things that we've written here are actually arbitrary, it's true that AB squared plus BC squared will be half of AC squared plus BD squared. And one way you can show this is using the cosine rule. A challenge to those of you who are familiar with vectors is that you can also show this using vectors by letting one of the sides be a vector A, the other side be a vector B, and then the two diagonals be A plus B and A minus B. Let's move on to question 8. Suppose that sine of 45 degree minus x is minus 1/3, where x is between 45 degrees and 90 degrees. Find the square of 6 sine x minus square root 2. In such a problem, we are instinctively compelled to just use the identity on sine 45 degrees minus x and kind of hope for the best. Certainly, there is nothing wrong with that approach. However, it does seem that once you have gotten 6 sine x minus square root 2 squared as your final outcome, whatever we do with sine 45 degrees minus x will need to be dealt with in a rather uncomfortable way, because somehow we need to abstract out the value of sine x from that. Instead, it is better if we restate this condition using the substitution theta equals 45 degrees minus x. And this is a general problem solving principle. Instead of starting with a condition that is not so nice and try to get to something at the end which is nice, it is easier to do it the other way, to restate your condition into a very nice statement like sine theta is equals to negative 1/3, and try to find something a bit more complicated, since that slightly more complicated thing would just contain many instances of sine theta and cosine theta, which we are able to find rather easily. So let's do the substitution here as well. If theta is 45 degrees minus x, that means that x is 45 degrees minus theta. So that means that 6 sine x minus square root 2 squared can be written as 6 sine 45 degrees minus theta minus square root 2 squared. Here we can apply the compound angle formula. So sine 45 degrees cosine theta minus cosine 45 degrees sine theta minus square root 2 whole thing squared. At this juncture, we can very quickly see we also need cosine theta. So let's come back to the left side. To find cosine theta. Now, can we say that cosine theta is immediately 1 minus sine squared theta, whole thing square rooted? The answer is yes, but often we need to check whether this cosine theta is positive or negative. Since theta is 45 degrees minus x, it means that theta is between negative 45 degrees and 0. And we know that for cosine, it is positive in the 4th quadrant. So therefore, we can say indeed that cosine theta will be positive, and it is the positive square root of 1 minus sine squared theta. So this would be square root 8 over 9, which simplifies to 2 root 2 over 3. Now at this point we are essentially done. We just need to be careful in calculating the rest, because sine 45 degrees is root 2 over 2, cosine theta is now 2 root 2 over 3, cosine 45 degrees is also root 2 over 2, and sine theta is negative 1/3. Now, simplifying all of these, the first term is just 4, the second term is plus square root 2, and you have minus square root 2. So in the end, the plus and minus square root 2 cancel out, and the final answer is 16. So for trigonometry, keep this in mind. If you can make the given condition nicer, perhaps do that first, because we don't mind making our final outcome a bit more messy, since it just involves multiple substitutions of the starting condition. Next up, we have question 9. If 8 cosine x minus 8 sine x equals to 3, find the value of 55 tangent x plus 55 over tangent x. Okay, so we have cosine and sine in a slightly unusual way as our given condition, and we're supposed to find out something about tangent. The general rule of thumb for trigonometry is that we can rewrite everything in terms of sine and cosine unless there is an obvious tangent identity, secant identity, and so on. Since tangent x plus 1 over tangent x does not look like any obvious identity to me, I'm going to rewrite it immediately as 55 times tangent x plus 1 over tangent x being equal to 55 sine x over cosine x plus cosine x over sine x. These two fractions, we can add them up. And lo and behold, we get our magical sine squared x plus cosine squared x. This is really a very commonly occurring expression when you're doing trigonometric simplifications. Remember that sine x and cosine x are always linked together by the fact that sine squared x plus cosine squared x equals to 1, going back to our unit circle definition of sine and cosine. As such, we can just say that our desired expression is 55 over sine x cosine x. So that seems a little bit closer to what we have on the left, which is asking us to deal with some given condition about cosine x and sine x as well. First thing about cosine x minus sine x is that, well, there's just a factor of 8 we can move to the other side. So let's write this as cosine x minus sine x equals to 3 over 8. How do I get to the point where I can state sine x cosine x equals to something? Well, one simple way to use the fact that you have sine x and cosine x in the same expression is that, once again, sine squared x plus cosine squared x is equal to 1. So we can square this expression with the knowledge that sine squared x plus cosine squared x is going to be gone anyway. So the square of 3 over 8 is 9 over 64, and that means that 1 minus 2 sine x cosine x is equals to 9 over 64. Rearranging and dividing by 2, sine x cosine x would be 55 over 128. And that means that my final answer is just 128. So take note of this very frequent occurrence of sine squared x plus cosine squared x equals to 1. The reason why it appears so often is that sine x and cosine x often come together in lots of identities. And so one of the ways to simplify many identities, or to get to an identity which we can use, is with this sine squared x plus cosine squared x equals to 1, which makes things a lot easier when we don't have so many high powers to deal with. Finally, question 10 asks us to find the number of ordered pairs xy, where x and y are integers, such that x squared plus y squared minus 20x minus 14y plus 140 is less than 0. This should immediately cause us to think of the equation of a circle, and it's kind of tempting, so let's see what turns out of it. X minus 10 squared and y minus 7 squared. Well, this is 100 plus 7, 149. Here we have 140, so therefore we are short of 9. Now what does this actually mean? Well, this is actually the interior of a circle. So whenever we see the equation of a circle, that's the circumference of the circle that we are really referring to. But when we have the less than, it means that the interior of the circle is what we're looking at. So it's the interior of a circle with the center 10, 7 and radius 3. When we are asked to then find how many ordered pairs xy are there in the interior of the circle, the number of ordered pairs of xy are integers is basically the number of points with integer coordinates, which is lattice points. So that's what ordered pairs xy, where x and y are integers, refers to. It is just lattice points. So in theory, one way to do this would then be to just draw it out. Let's take a point and draw around it a circle with radius 3. Try to count how many other points that are on the grid lines exactly give you a point inside the square, inside the circle, beg your pardon. However, that does seem like it requires us to have a piece of graph paper or a really good way of drawing a circle. So if we do not have any geometric tools with us, what then can we do? Well, we can also interpret this just from a very logical perspective. We are looking at the sum of two square numbers being less than 9. If the sum of two square numbers is less than 9, it means that each of those square numbers can only be 0, 1 or 4. It can only be 0, 1 or 4, and any combination of them would work because the largest of these, 4 plus 4, is just 8. And so that means that x minus 10 can be 0, plus or minus 1, or plus minus 2. And similarly, y minus 7 would also either be 0, plus or minus 1, or plus or minus 2. And those are all the combinations you have. So counting this is relatively simple. You have 5 choices of x, you have 5 choices of y, and therefore the number of pairs is just equal to 5 squared, which is 25. So that brings us to the end of this video, and in the next video we will be looking at questions 11 through 15, which will probably be a little bit more exciting than the ones we have seen so far.